So welcome everyone. Uh, Thank you for coming to our second talk in our seminar series. So before starting, I would like to let you know that we opened our YouTube page. Its title is Quantum Theories of Fields, Matter, and Strings. If you would like to catch up with our talks, you can subscribe to the channel. So in our second talk, we are excited to host Mithat Ünsal. Mithat is a professor of theoretical physics at North Carolina State University. He will talk about his recent work on the phases of theories with discrete one-form symmetries and its role in confinement. So Mithat, thanks a lot for accepting our invitation. We are very happy to have you today. You can start your talk.
Okay, thank you very much for the invitation, first of all. And so I will talk about phases of gauge theories with one-form symmetries, and I will specify more precisely the class of theories that I will deal with. And this is a work based on with my collaborators and close friends, Mendel Guen and Tin Süleyman Pasic. Okay. So first, let me give a little bit historical background on the predominant mechanisms of confinement. In the mid-70s, people came up with the ideas of the dual superconductor, where magnetic monopoles and their condensation in four dimension was responsible for the formation of confinement and for the generation of electric tubes in the say Young-Mills vacuum, gauge theory vacuum. These are the classic references. And what happens is that the condensation of the magnetic monopoles leads to dual Meissner effect. This is very similar to superconductivity, where condensation of the Cooper pairs leads to Meissner effect. However, this was a picture. It's a very very reasonable picture, but the mathematically precise formulations of these ideas came a bit later. Actually, Polyakov's work is again from mid 70s. Polyakov on R3 three-dimensional space in Young-Mills theory plus an adjoint Higgs field. This is called Polyakov model. He showed that proliferation of poles, which are in 3D space instantons, so they are events in space-time. They do not have word line. So the proliferation of the monopoles can generate mass gap and confinement. In four dimension, the first realization of this idea came with the work of Seiberg and Witten. They showed that in n equal 2 supersymmetric Young-Mills theory, if you break it softly to n equal 1, monopole or dione condensation leads to confinement. And here, monopoles or diones are genuine particles, and we are really talking about condensation of them. And there is, in a QCD-like theories, both of these theories have fundamental scalars in it. In QCD-like theories, a progress in this direction came in this work on QCD adjoint on R3 cross S1. Here, S1 is not thermal compactification. This is very important. Otherwise, certain conditions are not satisfied. And here, the objects that we can call monopoles or their correlated event called magnetic bionds leads to mass gap and confinement. You can show these things rather explicitly. Now, this is the picture about monopoles, what we know analytically about monopoles. Now, there is a competing picture. It's called center vortex mechanism. It also originated from 't Hooft, like many interesting ideas in our field and others. And the main idea is following. Here we are talking about a codimension to objects in d-dimensional Euclidean space-time. So depending on dimensionality of space, this object can be point. In two dimension, it's a point. It's therefore two Euclidean dimension, it's a point. Hence, it's an instanton. So three dimension, it's a line, and four dimension, it is a surface. So if you want to think in Hamiltonian picture, in three dimension, it's like a particle, a zero-dimensional object really, and in four dimension, 3 plus 1 dimension, it's a line whose world volume spans the surface. Okay, and so this is something that you have to keep in mind. These objects can have non-trivial linking with lines in any dimension. For example, a point can have a non-trivial linking in two dimension with this line, or if you are in three dimension, two loops can have non-trivial linking with each other. And the main property of these objects is that they have non-trivial mutual statistics with the Wilson loop. So if you calculate Wilson loop around this object, it will give you a pure phase, classically. And presumably the proliferation of these objects signals onset of confinement. This is quite favored in some part of the lattice community. However, there is no analytical treatment, but at least more recently, exactly in two dimensions, but not in higher dimensions, there is analytical confirmation of this picture in the work I did with Yuya Tanizaki. Okay. Now, let me state the intuition behind the center vortex, why we think that it may signal confinement. So when a discrete zero-form symmetry is spontaneously broken in any dimension, there will be domain walls between the vacua, and the restoration of the symmetry can be seen when these walls become light and proliferate. You can see these things very explicitly in some numerical simulation, for example. So center vortices are meant to be for center symmetry what domain walls are for discrete zero-form symmetry. In principle, at least as a thinking, they are heavy when the center symmetry is spontaneously broken, and their proliferation, again, allegedly signals the restoration of the center symmetry, hence onset of confinement. Certainly, with the proliferation of the center vortex, there is something interesting happening. And however, whether this is really a transition to a confined phase, it's a different story. I will come to that. Now,
Can I ask a
I
question?
have to make some, sure.
So are these domain walls charged under a d-1 form symmetry?
Domain walls here, I'm talking about only zero-form symmetries.
So, but usually when we have like a d-1 form symmetry, the charged object is something like a domain wall, right? Can we say that there is a symmetry acting on that? Or it's not something like that in this case?
At least, yeah, for my purpose, this is not very important. Maybe, yeah, I'm not sure of that, but yeah. But for whatever it is worth, for example, when we consider the system at finite temperature and talk about restoration of symmetry, if you stare at a simulation, you see, in some sense, these boundaries becoming light and proliferating.
By the way, Zohar made a comment. So he says that they are dynamical, so they have finite mass and they are not charged under an extended symmetry. And only non-dynamical objects can be charged under high symmetry. Okay. Thanks for the comments.
Okay, thank you. Now, let me tell you why our lattice friends thinks that they may, at least some portion of the lattice community, not all of them, think that they are very important. So as I said, these lattice, the understanding of domain of the center vortices are based mainly on heuristic arguments and numerical studies. Lots of people, and some of them, I know them in person, I trust them, and they will tell you the following. If you do simulations, if you take vortex only configurations, you can show that they account for confinement, deconfinement, chiral symmetry breaking, all interesting stuff. If you remove center vortices, none of these properties are present, okay? They will also tell you that we cannot show any of these things analytically because they do not lend themselves to an analytical treatment. Now, however, this seems to be as opposite to be what we know from calculable continuum theories. When I was talking about Polyakov model, Seiberg-Witten theory, or QCD adjoint on R3 cross S1, there isn't even a mention of the word center vortex, And to my mind, this is an interesting puzzle, important puzzle, and it's a conflict between a numerical experiment and theoretical idea, and it's something that needs to be understood more precisely. Of course, one attitude is to be dismissive about numerical data and not care.
Sorry, I think we have a question in the chat. So someone asked, is this related to Weinberg-Witten theorem? I think they were talking about the previous discussion.
Which one?
I think the previous slide. I'm not sure.
I'm not sure if it is relevant.
No, I was asking, I think Zohar said only non-dynamical objects can be charged under higher symmetry. Is this because dynamical things having this higher form symmetries generate some sort of gravity? With this, I think Weinberg-Witten theorem is about this, right? You have sort of this gauge symmetry that is higher form, or maybe I'm mistaken. I don't know.
Zohar, can you make any comments on that?
I just meant that the Wilson lines are charged under one form symmetry because they represent excitations that don't exist in the system, while domain walls represent excitations that do exist in the systems. These are just the confining strings.
Yeah.
I see.
Yeah, depending on circumstances.
So your proposal is, if I understand, is to measure the center vortex proliferation rather than the Polyakov loop. Is that the idea?
So my proposal, I will come to it, is to consider a framework in which I can consider both center vortices as well as monopoles simultaneously, and I can manipulate them simultaneously, theoretically. So, yeah. Okay. Of course, my intention is that try to understand both continuum theories as well as lattice theories from, for me, they are on the same footing, okay? So, as I said, we need some new methods, and this work is a step in that direction. And So what we will do is we will do something like, it will resemble to an effective field theory of ZN1 form symmetry, but it is not precisely a top to bottom construction of effective field theory. We will start with a theory in which there is a ZN1 form symmetry and use this idea of deformation class. I will tell you what it is exactly, and go explore all possible phases of the theory. Okay. So what are our assumptions? So we consider theories in which we assume that the underlying microscopic theory has only ZN1 form symmetry and time reversal symmetry. So Poincare symmetry can be exact or emergent, hence in the IR, so the formalism can apply to lattice gauge theory. Some of these assumptions can be relaxed for generalization. For example, this doesn't allow for chiral symmetry, but in this class of theories, there are many interesting gauge theories. For example, ZN lattice gauge theory is in this class. Yang-Mills theory is in this class. You can add Yang-Mills theory to some adjoint scalars and deform it to, to theories which will satisfy this thing. You can add Yang-Mills theory adjoint matter if you wish. Okay. Now, so let me tell you a little bit about this ZN1 form symmetry. So the cleanest definition of one form symmetry, so this is the symmetry under which the line operators are charged, and of course, we know historically that Wilson loops are used as a probe for confinement. A more precise understanding of this is that these objects are charged under the one form symmetry. So we can ask the following question: what are the possible phases, generic phases, not possible, generic phases of the systems whose only microscopic symmetry are ZN1 form symmetry and time reversal symmetry? I took time reversal because we didn't want to deal with some topological terms which may violate time reversal. So the strategy will be the following. We will start with some phase with broken ZN1 form symmetry. That is what is called a Higgs phase, or equivalently topological BF phase. I know that most of my audience are students and they may not know about topological BF phase, so I want to make a very short introduction to that by using charge n abelian X model. Okay, let me be specific to 2 dimensions here. It doesn't really matter for the purpose of this discussion. So in 2 dimension, you can consider a Higgs and abelian gauge fields. The charge of the Higgs is n. You have a potential like this. You may or may not add a topological theta term. It's not important. So the classical vacuum of this is given by this wave V, and there is a circle worth of vacua. So if you assume that you are deep in the Higgs phase, you can assume that the modulus of the Higgs field is frozen. So the kinetic term becomes of this form. Okay. Now, you can introduce a vector field B mu to rewrite this kinetic term. This is the kinetic term. This is same as that kinetic term, to rewrite this kinetic term in this form. Of course, if you integrate out this vector field B mu, you will land back on the original description, okay, if you integrate out B mu. But instead, if you integrate the phase of this Higgs field, then it will give you this constraint, which may be solved as shown here, where this var phi, let me call it phi, is a 2 pi periodic scalar. Then inserting back to the action, you see that there is a gauge kinetic term, Maxwell term, kinetic term for compact scalar. This is the BF term, and this is the theta angle. You can set this to 0. If you take the coupling to infinity, a gauge kinetic term dies, and And you can use the equations of motion of A to show that essentially P is frozen. That means the kinetic term, you can forget about the kinetic term in that domain. So in that limit, I am also setting theta to 0. In that limit, the theory reduces to this PF theory. So this PF theory has n-gapped vacua with spontaneously broken one-form symmetry, and these are the vacua. One can also start with this Lagrangian and actually integrate out gauge field itself, and that is even more concrete. You know, you can integrate gauge connection on some to manifold M2, but you can rewrite the integral over gauge connection as an integral over field strength, but you have to take into account that there are infinitely many flux sectors. And by using Poisson resummation, you can rewrite this as such. Then this integral essentially becomes a Gaussian integral. There is an f square here, f here, f here. And it's a simple Gaussian integral. You can do it. You see that as you take e to infinity, the mass of the scalar becomes infinite. And the scalar is pinned, set theta to 0 again, is pinned one of these n gapped, is pinned one of these vacua, and there are n of them. Now, this is how BF theory emerges from abelian charge n abelian X model. In more generally, in D dimension, this is the definition of the BF theory. There is a one-form field, and there is a D-2 form field. In 2 dimension, D-2 was 0, so there was a 0 form field, which was this scalar here. Okay. And you can show that this has Lagrangian has two symmetries. One of them is this Zn1 form shift symmetry, and the other is this Zn shift symmetry associated with this D-2 form. And the basic correlation function gives you this main phase vector mutual statistics between these two. Okay, where here V is, if you are considering the theory on some manifold M, V is some D-2 cycle and C is one cycle. If you are considering the theory on R to the D, these are essentially boundaries. However, you note that in my microscopic theory, there is only Zn1 form symmetry. But if I look to this BF theory, there is this extra symmetry. I do not want it. Okay, I should get rid of it. So this is not assumed microscopically. So what we can do is we can introduce objects with gate charge coupled to these fields. And these objects are codimension 2 objects. So they are points in 2-dimension, lines in, let me say Minkowski, lines in 3 Euclidean dimension and surfaces in 4 dimensions, okay? So we can introduce these objects. However, introducing them, I will come back to this, gives some extra unwanted continuous symmetry in particular in D equal 3 and 4 dimensions. And this symmetry, you can actually show that you can get rid of this symmetry by introducing monopoles. I will make these things very precise in particular examples. At this stage, it's a little bit abstract.
Sorry.
So in this story, yeah.
Sorry, yeah, I have a naive question. Like, why was this extra symmetry, I mean, undesirable? Can you not have an emergent symmetry happening at the broken face?
Oh, of course you can have it. But the idea is, we assume microscopically we have this Zn1 form symmetry, and the theory, we assume that the theory can always be made to land on this PF phase, a phase in which Zn1 form symmetry is broken. But this PF Lagrangian has this extra symmetry. And we want to think about deformations of this theory in which we only have this one-form symmetry. Of course, it can be an emergent symmetry in one particular phase. Okay, indeed, if you are in the Higgs phase, deep Higgs phase, it will be so. But we want to explore this is the idea of deformation class. We want to explore all other possibilities respectful to ZN one-form symmetry. Is that okay?
Yeah, thanks. Cool.
Okay.
Can I ask a question?
So
in
yes.
this deformation class, what kind of deformations do we allow? Like only topological deformations,
I will come
or
to
like
that.
any kind of?
I will. No. The rule of the game is that to begin with, you have this extraneous symmetry. Get rid of it. But when you get rid of it, you will give birth to some other symmetries and get rid of them. Okay? Get rid of them as much as possible. Then identify what objects, by introducing what you get rid of them. It will turn out that in 3 and 4 dimensions, you get rid of these things by introducing either center vortices, both center vortices and monopoles in 3 and 4 dimensions. Okay, this will be much more clear based on examples. So we will have theories in which we will have both center vortices and monopoles. And these deformed BF theory, the possibilities will be the following. Neither vortices or monopoles proliferate. This is a possibility. Both vortices and monopoles can proliferate. This is another possibility. Vortices can proliferate, but monopoles do not. This is also another possibility. Note that there does not exist a phase in which monopoles proliferate, but vortices do not, because if vortices are heavy, so are the monopoles by construction. Okay. Now let's go to examples. Okay. So D equal to dimensions. Okay, we show that to all orders in perturbation theory, for the abelian X model, we land on this BF theory. Okay, now I replaced phi, var phi with B. Okay, so the symmetry is there is a ZN1 form symmetry and ZN0 form symmetry. In this case, vortices are instantons and monopoles do not exist. Okay, and we want to break these ZN0 form symmetry, and I want to add operators exponential IB, which break these zero form symmetry. I'm sorry, ZN0 form symmetry, which break this ZN0 form symmetry explicitly. These operators are relevant because their scaling dimension vanishes, and if you add these operators, you generate this. So you learn that the assumption of spontaneously broken ZN one form symmetry is not robust, because when this term is present, you induce confinement. I will tell you intuition behind it. This is very abstract for my taste, okay? So I want to map what this means to the language of statistical field theory, and here what it is. So this insertion of this operator means that we are considering, for example, if you take a slice of the vacuum manifold, we are considering proliferation of these vortices, vortex, anti-vortex, these colored things, okay? So you can expand these exponents in the Lagrangian, and you can see that partition function can be viewed as a grand canonical ensemble of these vortices and anti-vortices. And so the correlation function is trivial, and you can sum it up, and you obtain the partition function as a sum over these m branches. Okay, so in some sense, the path integral localizes to the classical solutions of A equations of motion. So you obtain this partition function. But now what will happen when you insert a Wilson loop? When you insert a Wilson loop, if you have a vortex inside, it will pick up this phase, Wilson loop, and anti-vortex, it will give you this phase. And this extra phase is due to mutual statistics of the Wilson loop with the center vortex, okay? Now, when you look to this correlation function, it will give you these extra phases, and you can do this calculation, and you can show that this will generate a finite string tension, and this string tension only depends on the anality. So these non-trivial phases plus proliferation of these objects are finite action. That means they have a finite density in the vacuum, leads to finite tension, finite string tension. So will this be same in higher dimension, with the vortices in higher dimension? Okay, so that's the main question. But we learn here that, by these operators, vortex operators, which are there in this case, by the proliferation of these objects, we generate confinement. I didn't mention, but you also generate things like fractional theta dependence and stuff like that. Now, this was 2-dimension. Let me go to more interesting case of 3-dimension. Okay. Again, you start with BF theory, but now symmetry is usual one-form symmetry and this extra one-form symmetry. In this case, vortices are particles and monopoles are instantons, okay? So we want to break this Zn one-form symmetry, and to break it, we introduce a complex scalar with unit charge under this gauge field, okay? We introduce this. And we also write down a kinetic term. Kinetic term will nonetheless be generated. But you can show that when you do this, you gain a U1 zero form symmetry. This is the reason for this is following. Okay, the reason for this is that if you had a monopole in the original BF theory, you can show that the you can show that the BF action is not gauge invariant. If you have a monopole here, then you can show that it's not gauge invariant. But now, if you have a monopole in this theory with this extra scalar, you can actually dress the monopole with this scalar and with the junction of n of these things, and these objects, m tilde is perfectly gauge invariant. Okay. Now, what does it tell us? So, however, this now this we have this U1 shift symmetry, but we say we want to get rid of it. So this symmetry is in some sense forbids monopoles, okay? So we deform the Lagrangian by adding these monopole operators, dressed monopole operators. So we also added some kinetic term for gauge field. This will be generated nonetheless. And here is the thing. So we end up, with the most general case, we end up with a Lagrangian like this. Now, let us examine this carefully. If this phi field is heavy and it doesn't get a vacuum expectation value, you can drop it. Drop this phi here, drop it there. And so then this term is more relevant than these Maxwell terms, dV square, dA square. And deep infrared, you land on the BF phase. Okay, and indeed you have that emergent symmetry, as there was a question about it. But now the interesting situation is if this phi field condenses, if the center vortices condenses, then if they condense, this monopole operator becomes just like regular monopole operator. B field acquires a mass. I need to drop this thing, and the first term. Oops, sorry. So what is left is Maxwell term and monopole operators. But this is nothing but Polyakov's compact QED, and it generates confinement. This is interesting. Good, we have these two options. Although it is not generic, we can do the following. In this model, let's still assume phi condenses, okay? By the way, this is the, okay. Okay, I'll come back to this. Let's assume that phi condenses, but let's also assume that we have this shift symmetry. This shift symmetry prohibits monopoles, okay? But phi still condensed. So hence, in the system, we do not have monopoles, but we have vortices. So this term is gone, but the only thing we have at our disposal is this Maxwell term, pure Maxwell. So in this case, for example, if you are considering something like Zn lattice gauge theory, you would end up with a phase transition from BF phase to Coulomb phase. I will explain this thing in more detail, more intuitively. But when the monopoles are present, according to the rules of the game I mentioned, they should be present. If I just have my construction such that only one form symmetry is kept in the, then we will have PF phase and confined phase, okay, as possibilities. But now I want to say a few things here.
Can I ask a question
one of the things that, yeah,
so
it's still about the same thing, yeah.
Okay, so in the previous slide, you have this BF model and then you deformed it. So using the ideas of particle vortex duality, can we find a dual version of this theory that is fermionic and understand the phases of that theory in terms of what you understand in this theory?
That's interesting, actually. Possibly one can make something there, yes. Yeah.
Do you have any guesses as to what kind of a fermionic theory
no,
this would be due to?
At this stage, no. You
Okay.
have to tell me that.
Okay.
But I can tell you, I can give you more intuition about this theory. One of the things that I like most in StatMech is this Peierls instability type argument. Now, actually, this is something very interesting because the stuff, okay. So if you take a loop, minimal vortex loop of length L, you can calculate its action. Its action is beta 1 this is in Zn lattice gauge theory, okay, in 3D. Its action this part comes from the action, and this is the length of the loop, okay, energy times length, this is the action. Now, you can ask how many loops are there starting and ending at the same point, non-backtracking loops of length L. And you can actually count them. You can give a upper bound, lower bound, and a very reasonable estimate for number of non-backtracking loops in D dimension is exponential of log, in 3 dimension log 5 times L. You can think this factor as the entropy factor associated with this loop. There are this many loops in the game with this property, okay, starting and ending at the same position, a fixed position, but having length L. Now, if you write down single vortex contribution to the partition function. It will be this action versus entropy. You see that if beta is larger than some beta critical, this Boltzmann suppression wins. Hence, the bodies do not proliferate. Okay. This is the BF phase. The vortices are very short. They are dilute. Here, there are these loops of various kinds. But at beta critical, which goes like this, something interesting happens. The entropy factor wins. That means that when this beta inverse of the coupling is sufficiently small, the entropy factor will win, and there will be a phase transition. In the past, people interpreted this as a phase transition from the Higgs phase to Coulomb phase, to confined phase. But in this thought experiment here, I can get rid of the monopoles throughout the story, and the phase transition is still there. And the phase transition here is really from the Higgs phase to a Coulomb phase. So if you get rid of the monopoles here, despite the fact that vortices proliferate, and despite the fact that they have these non-trivial mutual phase with the Wilson loops, you land on the Coulomb phase. So in some sense, yeah, if you project out monopoles reliably, and you can do this by using Blaine formulation or something like that, you will land on a Coulomb phase here. Is this clear? Okay. And actually, there is a, I forgot to insert it, but there are very nice lattice simulations by Kreutz and Bano, okay, in which they determine this beta critical. And this log 5, you see, if n is large here, you will have a beta critical, which is log 5 divided by 2 pi square, log 5 n square divided by 2 pi square. Okay, and this thing is proportional to n square. As n goes to infinity, of course, the Zn lattice gauge theory becomes U1 lattice gauge theory, and this phase transition point moves to very large values. And in particular, when we are talking about, for example, Polyakov model, which is U1 lattice gauge theory, there isn't a BF phase because it is gone. Okay, this point moved to infinity. And in particular, if you take, for example, even compact QED, which is confining, in 3 dimension at any value of pair coupling, and if you remove the monopoles, then you will land on Maxwell theory. There is no doubt about it, So by just abelian duality will map Maxwell term to some kinetic term for the compact scalar, and you are done. But in my opinion, this is a very nice example because it's very concrete. You can calculate everything and show that indeed proliferation of these vortices is related precisely with this phase transition, and only when you allow the monopoles, this would-be Coulomb becomes a confining phase. Okay. Now, let me go to more interesting case of 4 dimensions. So in this case, we have Zn1 form symmetry and we have Zn2 form symmetry. vortices are strings and their world volume are sheets, and monopoles are particles. So we can break these to form symmetry by introducing vortices with gauge charge 1 and coupling it to these B fields. Again, we gain an unwanted U1 symmetry. This is the same in 2 plus 1. This was 0 form symmetry, but in this case, it's a 1 form symmetry. And we will break it by introducing a gauge field, associated with it. Then there will be 3 possibilities. One of them is vortices will be heavy, then we will land on the Higgs space. The other possibility is vortices proliferate and monopoles also proliferate. We will land on the confined phase. And another possibility is vortices proliferate and monopoles are heavy and we land on Coulomb phase. And I will show some recent simulations on that done by Tin and his friends. Okay. Again, if we take Z and lattice gauge theory, this is very standard, so I move over it quickly. In Wilson formulation, we have these link fields, Z link fields. And one interesting question is, for example, does the Z gauge theories on lattice have photon phases? It's a very intriguing possibility. And we can talk about the center vortices where plaquettes have this particular phase. Or we can go to Villain formulation, which is much more friendly for our purpose, which also makes monopoles manifest. The oriented sum of these MPs here, these fluxes, gives us the monopole currents, okay, or monopole charge or currents, the way you look at the construction. So you have both of these things in our disposal. Now, let's do the following. Let's work with Villain, and we want to isolate vortices from monopoles. So we can eliminate monopoles completely by introducing a Lagrange multiplier. This is a continuous field. It's a Lagrange multiplier. But when we do this, we gain this shift symmetry, vectorial shift symmetry, which is a one-form symmetry. And we can ask, we eliminated monopoles, what happens when the vortices proliferate in the beta goes to 0 limit? This is the strong coupling in this original formulation, strong lattice coupling under normal circumstances where we did not eliminate the monopoles. This is certainly confining. Okay. Now we can do some exact lattice manipulations. So this is an exact lattice duality, which involves Poisson resummation. So this is the Villain form. Modified, this part is Villain. This part is, I introduced the Lagrange multiplier, the theory from the previous page. Note that the gauge field, dynamical gauge field, is discrete, and Lagrange multiplier is continuous. By Poisson resummation, which is an exact lattice duality, you can map this thing to this form where beta is taken to 4 pi square over beta. Now the dynamical field becomes A tilde, and the Lagrange multiplier is now discrete. Okay, but now let us look at this carefully because something interesting happened. So we learned that the dual of this Zien lattice gauge theory with this modified Villain action is a U1 gauge theory. This is a U1 gauge theory. However, with magnetic matter of charge n, we see that charge n, because this is this is Zn values. So it projects out all the magnetic matter with charge, which is not multiple of n. The only thing that remains is magnetic matter with charge n. So, and in the dual formulation, gauge coupling is now beta. So when we consider beta goes to zero limits, we are really talking about weak coupling limit here. While beta goes to zero limit here was very strong coupling. Okay, we have very weak coupling beta in the dual formulation, and we only have charge n monopoles which are super heavy, and the existence of the Coulomb phase is manifest. They cannot do anything. They cannot proliferate. Okay.
Sorry,
So something very interesting.
question.
Yeah.
So is this like some sort of generalization of the Kramers-Miners duality you have for the Ising model? Or no?
I would, in some sense, yes. It's a duality between a z. Yes, actually, the answer is yes. More precisely, it is between Zn clock model and U1 XY model with charge and global vortices. I think this is correct. Yeah. The two-dimensional version of this is well known, maybe from the work of Kadanov and others. Yeah. Yeah.
Here you're in 4 dimensions, so I think it would be some kind of high dimension generalization, I guess.
Yeah. It's a high-dimensional generalization of that, but it is all of these things is a rather straightforward application of this Poisson summation. Actually, it's not. It's relatively easy, honestly. Yeah. But the outcomes, when you think about it, the outcomes are non-trivial, because here, we learn this thing. For example, we learn these. If you open any standards lattice gauge theory book, they will take beta goes to zero and they will show you confinement analytically all the time. They can use either tiling of the Wilson loop, standard strong coupling expansion, and it is true. Okay. The surprise here is that in that beta goes to zero limit, which is the strong coupling of the original theory, when you get rid of the monopoles completely, you can map this theory to a weakly coupled theory, U1 gauge theory. And here with charge n monopoles, but charge n monopoles here, because of the weak coupling, they are super heavy and they do not proliferate. Hence, this is really in the Coulomb phase, Maxwell phase. This is the surprising. So you learn that strongly coupled, infinitely strongly coupled lattice gauge theory is in actually Coulomb phase. This is, for a lattice person, this should be relatively surprising. Now, we can play the following game also. We can reintroduce monopoles to the story, but make them heavy. Okay, this term explicitly breaks this shift symmetry. And in the original dual description, we have a U1 gauge theory coupled to charge n monopoles. And well, I call this electric matter, but I introduced these new dynamical monopoles as well. I sort of called it electric. Maybe it's not a good habit, but remember that in Seiberg-Witten theory, if you consider, for example, monopole point or dione point, you are talking about an SQED, and strictly speaking, the electrons in code there are monopoles. This is the sense in which I use this language, I think. So if these monopoles are heavy, this Coulomb phase persists, okay? So this is some sort of, But so this is my deformation. If actually, this part of this phase diagram for n greater than 5 was known in the past. So without this, so we land on with the following possibilities. If n is greater than 5, you go from BF phase to Coulomb phase, even when this mu is very small, and then you can go to a confined phase. For
Mithat,
n equal to 3 and 4, yeah.
did you try to measure the fine structure constant in your Coulomb phase?
We didn't, but Tin measured the correlation functions which would give, for example, Coulomb behavior. I'll come to that in a moment. For example, F correlator, you can look at it. It has to go as 1 over x to the 4 in the Coulomb phase. They measured it in their most recent paper. I will make a remark on that paper.
Thank you.
But even for n equal 3 or 4 of the Z gauge theory, if you crank up this deformation parameter, you will again land on the Coulomb phase. Okay, at arbitrarily strong coupling, you can land on this Coulomb phase. Okay. Now this is of course theory, and there is this very recent paper by Jeffrey. It's interesting what life brings. Jeffrey and I were friends in grad school. We haven't seen each other for more than 20 years, and now, but he was a mathematician, and we used to help each other in our retrospective fields. So, and he was undergraduate, more to say, in Seattle, but now they are colleagues in Durham with Tin, and David is Tin's student, and they did these beautiful simulations. Okay, so here is the thing. So these are Polyakov loop. Okay, this is the Polyakov loop and some set up for the configurations, and this is Z7 lattice gauge theory. Okay, this is 0 expectation value for the Polyakov loop. It's the confined phase. So this is 1 expectation value for the Polyakov loop. It is the BF phase, Higgs phase. And there is something happening in the middle there. And so I just grabbed this morning from Tin's paper. So let me look at it. Okay, so I know it, but okay. These are center vortices, but they are very dilute, very small in their construction. And these green points, yellow points are monopoles. And you see that in this first phase transition where there's this discontinuity, vortices proliferate, but monopoles do not. And here, actually, in this phase, answering Zohar's question, they actually measured correlation function of field strength correlation functions, and it has to decay something like 1 over x to the 4 with some structure up there, and they see it perfectly nicely. But then they go even to stronger coupling, and they land on this phase where monopoles also proliferate, and they see this confined phase. Okay. They did other simulations. They did for n equal 3, which is more interesting case in certain sense, because here in the n equal 3 case, without this suppression, suppression of these monopoles, you go from mixed phase to a confined phase. But when you suppress the monopoles, you go to a Coulomb phase. And they played very similar games somewhere, for example, at a slice like this, and they see both of these phase transitions. It's a very, very nice paper. It just appeared last week. I strongly recommend you for you to look at it. And also note that here only the minimal center vortices are there, and minimal center vortices proliferate, but here center vortices become plentiful, so they proliferate very easily, and even vortices with charge Q, 3, so on and so forth, they proliferate a lot. Now, actually, I have some more stuff, but I don't want to take too much time. I can give a summary and stop here. I think that this set of ideas may resolve a number of difficulties between continuum calculable theories and lattice numerical experiments. And long time ago, this is a sentence that I didn't come up with. This is a sentence that a lattice friend of mine who work on this center vortices, he said that the center vortex removal procedure is same as throwing out baby with the bathwater. You know, when people essentially remove the center vortices, they also implicitly remove the monopoles. Hence, you do not get. Hence, you know, some of the conclusion you reach is sort of vague or plagued a little bit. It is you from this analysis actually you learn the necessity of the center vortices, but not sufficiency. So only in 2 dimensions, this proliferation of center vortices is sufficient, both necessary and sufficient to have confinements. In 3 and 4, the phase in which center vortex proliferate but monopoles do not is Coulomb phase. And as I said, the center vortices is necessary because they are not sufficient to generate confinement, but they generate the right environments for the proliferation of the monopoles. If they do not generate this environment, monopoles cannot proliferate either. But even if they do generate this environment, monopoles may not still proliferate, okay? This is a different question. Hence, you know, the combination of these two is both necessary and sufficient. So as I said, if monopoles also proliferate or condense, depending on dimensionality on top of these vortices, this leads to the confined phase. And this last part I didn't talk about, but I don't have to. I think this was more or less the story that I wanted to tell. I can stop here.
Okay, thanks for the very nice talk. If anyone have questions, they can just unmute themselves and ask.
Oops.
Yeah, I have one if anyone else is not going.
Yeah, sure, you can go ahead.
Sure. Yeah, so I guess like my question is that like is it like your analysis, is it limited to flat spaces, or if we introduce some kind of curvature, will it still hold? Because from my limited understanding that curvature can affect phase transitions in some sense, specifically like if we go to hyperbolic spaces or something.
Oh yeah, curvature can certainly affect phase transitions. Actually, if you are considering, for example, gauge theory on S3 cross S1, you know, there is this nice work by Ofer, Aharoni, Shiraz Minwala, and others, where they look to the confinement, but you can also look in their setup to things like chiral transition, and you know, curvature behaves some sort of like temperature, and indeed there are chiral transition. But here, considering these setups, I don't know. You have to formulate lattice gauge theory first in these hyperbolic spaces and stuff like that. And these are not done. Some of the stuff in spaces with curvature are rather interesting, but for this kind of problems, I think we would be bad if we can get a hold of them, complete understanding of them in flat space, either on lattice or continuum. Go ahead, please.
No, sorry. I was just saying that, like, if it's, especially lattice theories on hyperbolic spaces will suffer from severe boundary effects. Like, I think there are some works by Richard Brouwer and the company on this.
Yeah. Okay. There may be phase transitions in hyperbolic spaces. It will depend on radius of curvature there. And that was sort of the point. But if we consider theories with only one form symmetries, for example, if you consider something like Young on ADS4, you are asking, right? So in that space, so what will happen? We can also discretize as desired if possible. You can even mimic it, even in flat space by playing games with the couplings on the link by some. But I don't know. Some of these things may hold because it is local dynamics, you would think. But some of these things, I'm not sure what would happen. But I mean, if the radius of curvature very small, then it should be like flat space, more or less. Even, for example, in gauge theory on S3 cross S1, if you take large S3 limits, you do get standard result on the flat space. So, yeah. I'm sorry, I don't have something very good to say on this.
Thanks for your answer. It's fine. It's it was just a speculative question. Yeah, because like when you said ADS4, I just realized that even like, so for example, if one, like, usually the Wilson loop goes from an area law to a perimeter law, and if your Wilson loop is large enough, these two things might not even have a proper distinction as well. So it might be a very difficult question to ask.
Yeah, on ADS4, as you play with the radius of curvature, there may be phase transition, and there may even be, it is possible. But there may also be, I don't know, for example, people also, for a very long time, people thought that on R3 cross S1, when you do compactification, there is necessarily a phase transition. But, especially in non-supersymmetric theories. In supersymmetric theories, we knew that we can avoid this. But the work I mentioned in the first slide on QCD adjoint was employing some different boundary condition on R3 cross S1, in particular periodic boundary condition for fermions. And in that case, you can show that there is no phase transition associated with one-form symmetry. So even on some spaces with curvature, you may have circumstances in which you may have adiabatic continuity. And if you can connect something strongly coupled to weak coupling, that makes it very, very interesting laboratory. Then you can try to tackle the problem by using the weak coupling methods like I did on R3 cross S1, for example. But it's an interesting question, the question you are asking.
Thanks.
Okay, any other question? If no one has, I will ask a question. So you mentioned the center vertices and monopoles. In D equals 4, we also have Yang-Mills instantons. How do they enter the story?
That's a super interesting question. Actually, I will tell you one more thing then. If you compactify Yang-Mills theory to R3 cross S1 and for example, deform Yang-Mills by using this double trace operator, then you can achieve adiabatic continuity between R4 and small s1. So that you can achieve absence of phase transition. Then you can ask, what happens to the 4D instanton, BPST instanton? What happens is that instanton fractionates to n monopole instantons, literally. And this is what I showed in the work with Larry Yaffe and Schiffman in 2007-8. And the proliferation of these objects or proliferation of the bionds generate confinement. So this is number one input. So instanton can transmute to something that you would call monopole instanton upon compactification. Now, if you do on R2 times T2, okay, with the insertion of 2 Hooft flux, you can again avoid phase transition as you go to small T2. And this is the work of mostly with Yuya Tanizaki, and I was also involved with it. And Yuya continued, and we are still collaborating. In that case, the instanton in 4D, which transmutes to monopoles on R3 cross S1, when you compactify one more, it transmutes to center vortices with short range interaction. Okay, so these center vortices, the objects that you would call center vortices in 2-dimension, and there are n types of them, each one of them topological charge 1 over n, each one of them a fractional action. These properties are identical to monopoles. They lead to confinement. Yet, this is very important, okay? Yet, most of the community thinks that instantons in 4D do not cause confinement, okay? This is more or less consensus for a very long time. You can read Coleman's book, it says whatever confines quarks, it is not instantons. Or you can look to Polyakov. He explains why. He's a brilliant man. These are brilliant men, and I have huge respect to them. And they explain why, he explained, Polyakov is very honest with his words, okay? He says why instantons disappointed him. My thinking is that we are super naive about our thinking concerning instantons in 4D, okay? We do not really understand them. We have to admit this truth to ourselves and try to make progress, okay? If the same object, you take the same object, if its fractionalization on R3 cross S1 causes confinement, mass gap, and all interesting non-perturbative phenomena, if you compactify on R2 times T2 and the fractionalization of the same object to something entirely different, vortex, with long short-range interaction, causes these effects, including fractional theta dependence, it tells me only one thing. We are being super naive about instantons in 4D, okay? In my opinion, instantons are very interesting beast about which we understood very little in 4D. It is very different from the instantons in quantum mechanics in Polyakov model. If you look to quantum mechanics or Polyakov model, an instanton, it has a moduli space, which is rather small. But the instantons in 4D, similar to instantons in CPN model, it has a moduli space, which is 4n dimensional, okay? It is a huge moduli space. To me, it tells me that there is some inner structure to the instanton waiting to be explored. I did something in this direction in 2D, in CPN, and I think that with Mendel, again, we understood great deal. But honestly, we posted this paper in 2023, and it's probably one of the deepest thing I ever did, and no one cared, and no one still cares. But I think once we understand similar structure for the instanton, they have to care. Yeah. For the instanton is a very interesting thing. We do not, So it can do very interesting things, but we do not understand them, and no book, no review approaches to the proper understanding of it.
So
there are
I
very
was
useful information
sorry.
Go
So
ahead.
I was thinking along the lines of your paper with Yuya Tanizaki on the four-group structure in Yang-Mills theory. So in that paper, you mix the Zn one-form symmetry with a Zp three-form symmetry. So when you study a BF theory that has this symmetry structure with a four groups appearance, what kind of phases would you get? Like, can we probe the phases of that BF theory?
That's a more formal question than remarks I provided. Okay, for my purpose, that doesn't matter because it's coupling a Yang-Mills theory to a topological quantum field theory, and it doesn't change local structure. Hence, from one point of view, one can say, nothing changed locally. So, but globally, things change. There is this interesting four-group structure. There are universes. There is interesting things happening. Can one understand something more from there? I'm not sure. Probably I shouldn't say this, but I was if I shouldn't say this, I shouldn't say this. Yeah, for me, it's interesting, but it would be much more interesting if it implied something for local physics. So, and concerning phase transition, because of that, I'm in doubt that things will change. Maybe
But when you have
globally,
the
some things can
mixed,
change. Yeah.
but the BF theory will change. I mean, you will not start from the same BF. You will have a different BF with, that captures the four-group structure, and then you will deform with centric vortices and monopoles. So
exactly. But this BF theory will even change. I consider, Yang-Mills theory with, instead of Yang-Mills theory, if I consider n equal 1 super Yang-Mills theory, then I will also have chiral symmetry to put into game. So I wanted to be very restrictive here. For example, why Yang-Mills can fall into BF? If you had two adjoint scalars, and if you give them vacuum expectation value, which is clock and shift matrix, then you can break SUN. With clock matrix, you can abelianize it. You can break it to U1 to n-1. With the shift matrix, with the both, you can break it down to Zn. Hence, for me, Yang-Mills theory with this, addition of some adjoint field can be transmuted to to Zn gauge theory, BF theory, okay, in the infrared. But of course, what you are saying is correct. When you have this four-group structure and, things about, you have to incorporate that to the BF theory construction. I didn't do that. I didn't even think about it, honestly.
So we have a question from, sorry. If you want to go on.
Yeah, go ahead.
Okay, so there's a question in the chat that I will read. So it's a follow-up question about the question I asked about particle vortex duality. Can we give topological or classical superconductivity as an example? If not, why proliferation procedure does not work for these models in essence?
No, you can give superconductivity as an example. Actually, this is the canonical example of So you know, if you write Landau-Ginzburg type effective field theory, you know, the Cooper pairs have charge Q. So superconductor in the deep infrared, it's actually Z2 BF theory to begin with. So that's a very good example. It's the canonical example. It is in the same category as my abelian X model.
Okay, so I don't know if that answers the question. I think it was Ömer who asked the question. Yeah. Yes, yeah. So any other question from the audience? Okay, we can stop the recording. Thanks again for the great talk. So